Hi, this is Xin Li from UC Merced. Today, I'm going to present our work, Neural Design Network, Graphic Layout Generation with Constraint. This work is done when I was an intern at Google Research. Advertisements are everywhere. How are these advertisements created? Usually, there are some common components, like images, logos, slogans, and descriptions. These components are placed following some design rules like alignment and aspect ratio. It looks easy, but it usually requires professional designer and is time and money consuming. Can model create graphic design? Graphic design surrounds us on a daily basis, from image advertisement, movie poster, and book covers to more functional presentation slides, website, and mobile applications. Graphic design is a process of using text, images, and symbols to visually convey messages. In graphic design, layout, the placement and sizing of components plays a significant role in indicating the flows of a viewer's attention and the order by which the information is received. Creating an effective layout requires understanding and balancing the complex and interdependent relationships among all visible components. Moreover, we would also like to enable flexible user control over the relationships among components. In this work, we aim to generate layout, that is, bounding boxes for all components, given desired components and user-specified constraints. Here's an illustration of a setting. Given one headline, two text, two images, and several constraints, we can generate various possible layouts. We also manually create final designs based on generated layout to better visualize the quality. We propose a multi-stage framework, Neural Design Network. The relation prediction stage aims to predict complete relations among objects. The layout generation stage aims to predict bounding boxes for all components. Finally, the refinement stage further fine-tunes the results. In the following, I will explain how each stage works in detail. In reality, for a design containing multiple components, usually only partial constraint will be provided. Therefore, we need to predict missing constraints. We use a graph to model the components and the relations among them. Each node represents a component, and each edge represents a relation between two components. Given a graph with several edges marked as an unknown category, we aim to generate a graph where all categories are known. Note that any graph with unknown edge category could generate various possible graphs with complete relations. To handle this one-to-many mapping property, we apply techniques from diverse image-to-image translations. We model the process as a graph-to-graph translations using paired data. The graph with complete relations is encoded to a latent space, which will be randomly sampled from in test time. Then, the graph with partial relations perform graph-to-graph translation conditional on the encoded latent space. In the layout generation stage, we have a graph with complete relations obtained from the relation prediction stage. We model the layout generation as an iterative conditional VAE process. At the beginning, we start with a blank canvas. Then, at each step, we predict the bounding box of a component. We perform conditional VAE for the prediction. The bounding box prediction is conditioned on the graph and a canvas containing previously predicted bounding boxes. Here is the formal formulation. Finally, since the previous generation is in an iterative manner, we do not have a chance to fix or improve previous generation. Therefore, we add a refinement stage to further improve the alignment and the visual quality. We use three different kinds of datasets: we collect an image banner advertisement dataset containing advertisement of vehicles. We use a RICO dataset containing mobile apps applications. And we also use the magazine dataset. We compare the proposed methods to previous work on 3 different settings. No constraint setting, that only components are provided. All constraint settings, that components and all relations are provided. Leave one out setting, that we predict the location of the last component given information of all other components. We use FID to measure the visual quality, alignment to explicitly measure the alignment among all components, and the accuracy specifically for the leave one out setting. For the quantitative comparisons, we perform comparably to previous methods on the no constraint setting, the all constraint setting, and the leave one out setting. We demonstrate the qualitative comparisons. In the all constraint setting, we can almost reconstruct the ground truth images. In the no constraint setting, we generate reasonable results in terms of visual quality and alignment. We demonstrate how we can handle user-specified constraints. Given desired components and user-specified constraints, we can generate layouts that look reasonable while conforming to the constraint. We also manually generate some design based on the generated layout to better understand the quality. Finally, we show an applications on layout recommendations. Given partial layout and desired components, we can perform recommendations with various example outputs conditioned on current partial layout. Thank you for your attention.